Welcome back to the properties of vectors lesson, and now we're going to take a look at a very interesting example. We're given 3 points in 3D, and we want to determine if the 3 points are coplanar, which means they lie on the same plane or not, by using the cross product. So imagine 3 points connected together, making a plane together, which means that the 3 points must make some triangle. I'm going to call them randomly as points A, B, and C. Now remember that if you cross product vectors A, B, and AC, then you would get a vector perpendicular to both of them, to AB and AC. So you will see a 90-degree angle in here. Now, if you had to multiply or to cross product vectors BC and BA, you would also get a vector that is perpendicular to both BA and BC. So if these 3 points lie on the same plane, that means that these two vectors must be parallel to each other. So in order to prove that the 3 points are coplanar, then we have to prove that the cross product of any set of vectors on this triangle will produce parallel vectors or collinear vectors. So let's get started. First, we need to find the coordinates of each vector that is made by connecting the points. So I will start with vector AB. Remember that this is the tail, this is the head. So from the head, subtract the tail. So that means that from the head B, we subtract the tail, which is at A. So 4 minus 1, that's 3. 7 minus 2, that's 5. And 0 minus 1, that's negative 1. Vector AC. Vector AC, again, C is the head, A is the tail. So from the head, subtract the tail. So 7 minus 1, that's 6. 1 minus 2, that's negative 1. That's a 12. So 12 minus 2, that's a 10. Next, negative 1 minus 1, that's negative 2. So we'll cross product AB and AC. So start off with IJK. List the coordinates. So 3, 5, negative 1, 3, 5, negative 1. The coordinates of vector AC, 6, 10, negative 2, 6, 10, negative 2. Remember, it's very easy to mix up the numbers here. Always double check before you proceed with the next step. So what I have in here is IJK. Next we have vector AB, 3, 5, negative 1, 4 minus 1, 3, 7 minus 2, 5, 0 minus 1, negative 1. And vector AC, 7 minus 1, 6, 12 minus 2, 10, negative 1 minus 1, negative 2. So the coordinates are listed correctly. Now we'll go ahead and we will do the product. So start with down products first, which means we have 5 times negative 2, negative 10i. Negative 1 times 6, negative 6j. 3 times 10, 30k. Subtract. Now we'll do the up product. So here we go. So up products go 10 times negative 1, negative 10i. Next we have negative 2 times 3, negative 6j. 6 times 5, 30k. Let's simplify. So remember that i's will go together, j's will go together, and k's will go together. So we have negative 10i minus negative 10i. So negative 10i minus negative 10i, 0i. Negative 6j minus negative 6j, that's very interesting. So 0j. And 30k minus 30k, oh, that's 0j. So let's move on to the next cross product. So we're doing now vectors BA and BC. We can choose any sets of vectors, basically. But I picked BA and BC. So we would expect the same thing to happen. So for BA, we have B is the tail, A is the head. So from head, subtract tail, 1 minus 7, negative 6. Again, from the head A, subtract the tail, 2 minus 12 is negative 10. And again, 1 minus negative 1, which is 2. So as you can see in here, BA is negative 6, negative 10, and then positive 2. Next, we'll continue with vector BC. So for vector BC, we have B to C, C is the head, B is the tail. 7 minus 4, 3. 12 minus 7. And then negative 1 minus 0, negative 1. So let's cross BA with BC. IJK, IJK, negative 6, negative 10, positive 2, negative 6, negative 10, 2, 3, 5, negative 1, 3, 5, negative 1. Draw the line. Down products first. 10i, 6j, negative 30k. Take away. Up products next. So 5 times 2, negative 1 times negative 1, 3 times negative 10. So in this case, we have 5 times 2, 10i, plus 6j, minus 30k. So 10i minus 10i, that's 0i. 6j minus 6j, 0j. 30k negative minus negative 30k, that's 0k. So in this case, the product was vector 0. The cross product produced vector 0, which is practically the same vector. So we're going to say that vectors AB and AB, AC, and BC will be coplanar, which means that points A, B, and C are coplanar. Next, we are given the statement that A plus B plus times A plus B equals A squared plus 2AB plus B squared. And you probably recognize here a very important binomial expansion, A plus B squared. Now we have to prove the statement by using the algebraic definition of dot product, because that's what we have in here. So in other words, what we have is A plus B dot in A plus B. So when you dot product the sums of two vectors, then we'll say that we have vector A dot A plus B plus vector B dot A plus B. In other words, we'll have in here A dot A plus A dot B. So we're using vector properties for dot product. B dot A plus B dot B. Now remember that A dot A, let's look at the property here. So we say that that's what we call the magnitudes property. That would be equal to the magnitude of the vector squared. And that's understandable when you look at the angle made between vectors A and A is 0. So cosine of 0 would be equal to 1. Now, when you say A dot B or B dot A, it means the same thing. So we're going to say is 2 A dot B. So we're going to say that A dot B on its own would be equal to, let me put this way, would be equal to 2 magnitude of A, magnitude of B, cosine of the angle between A and B. On the other hand, A times cos 0, that would be magnitude of A squared. Similarly, we say B times B cosine 0, that would be magnitude of B squared. So as you can see in here, in the middle, we have the term 2A dot B, and then we have A squared plus B squared. So this is how you prove this statement by using the dot product. Now, another way would be by simply letting A be represented by AX, AY, B by BX, BY, which means that A plus B would be AX plus BX, AY plus BY. So let's get to work. I'm going to make this a little smaller actually so that we have a bit more room. So what we are dotting here is A plus B and A plus B. So A would be AX, AY. Plus B, which is BX, BY. And that will multiply again AX, AY. These are coordinates. Plus BX, BY. So remember that these are coordinates here. And these are coordinates as well. So in order to add the two vectors, we have to do brackets first. So we'll say that AX, AY plus BX, BY would equal AX plus BX, and then AY plus BY. So these are the coordinates of vector A plus B, which multiplies itself AX, AY plus BX, AY plus BY. So we said that in dot product, we have to multiply the x coordinates together, the y coordinates together, which means that we're multiplying AX plus BX by AX plus BX. And we're adding, because it's dot product, right? Here, AY, BY plus BY by AY, BY plus BY. So basically what we are doing here is we're multiplying the x coordinates together plus the y coordinates together. So remember, coordinates are just numbers, so let's go ahead and multiply AX times AX so ax squared, and then plus, so since they are coordinates, we can expand it, plus 2ax bx plus bx squared. And the same thing will apply to the next expansion. So we have ay squared, but we have the y coordinates, right? Plus 2ay by plus by squared. Okay, so always keep an eye on where you're going. So you need a squared plus b squared. So we're going to combine the terms. So we have ax squared plus bx squared. And then we have 2ax bx, 2ay by. So we'll say 2ax bx plus ay by. So with this, we brought these two terms together right here and took out the coefficient of 2. The ax squared and bx squared are here together. And now we have the y coordinates. So ay squared plus by squared. So when you look at this term in here in the middle, ax bx plus ay by, that reminds you of the dot product a and b, because that's what you get in dot product. So we're going to say 2a dot b. So that's where this term here went. So this one is the same as this. Now remember that ax squared plus bx squared, ay squared plus by squared can also be rearranged. So we're going to say that ax squared plus ay squared will give a squared. In magnitude, obviously. And similarly, we're going to say that bx squared and by squared will give magnitude of b squared. And there you go. The statement is proven. Now we're going to use the vectors a and b with the given coordinates to practice the same formula. Now, but we are here in 3D. So you will be multiplying or dot producting vectors a and b, which means we have 1, 3, and 4 multiplied by -2, 5, and -1. So again, we're going to go x coordinates together, y coordinates together, and the z's together. So we have 1 times -2, 3 times 5, and 4 times -1. So -6 plus 15, the answer will be 9. Thank you for watching, and please follow with the next video for the lesson on properties of vectors.